So today's lesson is going to be about systems of two variables and solving for those variables. I'm not going to read this slide to you. If you want to pause it and read it now, you can. We're going to jump into some problems. Okay, so this first example asks you to solve the system of equations by graphing. So the first thing, it asks us to take one of the equations and rewrite it in slope-intercept form. So that means we have to move that 2x to the other side. Okay, and we're going to do the same thing for the other equation. I have to solve this for y, so we go ahead and do that. That becomes a positive 3/2 x minus 2. And then we need to graph those and see where they intersect. So I'm going to go ahead and do that. I graph those two equations. We have the one in blue and we have the one in red, and we notice that they intersect there at the point 2, 1. So that is our solution that works for both. Now, the next question here asks us, can we check our answers using algebra? We sure can. We can go ahead and substitute in the 2, 1 into this equation and make sure it works. And you'll notice that it does. And we'll do the same thing with the other equation. Y equals 3/2 x minus 2. And you'll notice that it works for the red equation as well. So that's a way you can check your work. Again, I'm not going to read this to you. We're now going to take a look at the methods that you learned to solve algebraically, substitution and elimination. So here we have an example of substitution. I'm not going to read that to you. You could take a look at it on your own time. We're going to jump right into some examples. So here it says that y is the same as 2x minus 9. So we are going to substitute that in where we see y in the other equation. So where that y was, we just put 2x minus 9 there. And then we go through and we simplify. So we're going to distribute. And then we combine like terms. And we subtract 45 from both sides. And x is going to be a positive 16. Now we're going to go ahead and take this equation, y equals 2x minus 9, and we are simply going to replace x with that 16 that we just solved for. So y is going to be 23. And sometimes you want to write that answer as an ordered pair, depending on how it's provided to you. Okay. I would like you to try this next example, pause the video, and then check your work with mine. So here we solved for x, and x was 5, and then we went and solved for y was 3. So we have 5, 3 is the ordered pair. So this next page explains elimination. It gives you an example. We're going to jump right in to example number 4. So elimination, we're trying to eliminate one of the variables by adding or subtracting the equations. All right, so this first one here, the first thing I'm going to do is I'm going to get rid of the x's because we have a negative 2x and we have a positive 2x. If we add these equations together, these cancel. So I have 3y plus a negative y is 2y, and 4 plus a negative 8 is negative 4. So y is going to give us negative 2. And then we're going to take one of the original equations, doesn't matter which one, and we're going to go ahead and plug that y in. And solve for x. So I have 2x plus 2 is equal to negative 8. 2x is negative 10. X is negative 5. Okay, so we have our x and our y. Again, if we want to write it as an ordered pair, we can. Okay, now this one I'm not going to have you do on your own quite yet. Right here, we're looking at the coefficients of x here. Let's try to make this a little bit bigger. These do not match. I have 1 and 3. And here I have negative 3 and 1. So right now, if I added and subtracted, nothing would eliminate. When that happens, you want to multiply one of the equations or both of the equations so you can get the coefficients to be opposites. So I'm going to go ahead and take that equation there, and I'm going to multiply it by a positive 3. Now, why would I choose that number? Well, if I do that, this equation becomes 9x plus 3y equals 12. Or excuse me. Woo, that was a common mistake. You multiply each one of these terms by 3. Then I'm going to take this original equation, and I'm just going to rewrite it down here. Now, if I add these equations, I get 10x. These now cancel each other, and I can simply solve for x. And now you do the same thing that we did before. You're going to pick one of the equations, and we are going to take 6 and plug it in and solve. I went through and solved that one. So we have 6, negative 6. So here we have some more problems. So we're going to write the system of equations and then solve. So let's go ahead and read this and see if we can decipher what we're being asked to do. Stephan's school is selling tickets to a concert. First day, ticket sales of 3 child tickets and 1 adult ticket totaled $38. The school took in $52 on the second day, selling 3 child tickets and 2 adult tickets. Find the price of a child ticket and the price of an adult ticket. So that informs us what our variables are going to be. So let's fill out what C and A are going to be. That last sentence told us that we're trying to find the price. So C is going to be the price of a child ticket and A is going to be the price of an adult ticket. So our equations, we know that 3 child tickets and 1 adult ticket cost $38, and 3 child tickets and 2 adult tickets was $52. So to solve this, we're actually going to subtract these equations. You don't always have to add them. We're just trying to eliminate one of the variables. So I've got 2a plus 3c equals 52, and I have 1a plus 3c equals 38. I'm going to subtract. So 2a minus 1a is 1a. These cancel. And here I have 14. Yep. So 1 adult ticket is $14. So if we want to find the child tickets, let's go ahead. We've got 3c plus 1a equals 38. Let's plug a in. 30C is going to be 24. So C is going to be $8. Adult ticket, $14. Child ticket, $8. I would like you to try example number 7 and then check in with what I did. So please pause the video and then check. So we set up the equations for vans and buses, wrote the equations, multiplied them by 2. We go through and subtract, and I've got 7b is 741. We go ahead and solve that, and we get 21 buses. 21 kids in a bus, and then you go ahead and solve for the number of kids in a van. And I ended up with a van carries 9 students. On this page, we are looking at some special cases where we could end up with no solution or infinitely many solutions. You can read this on your own time. I'm going to read this part down here. When solving special systems algebraically, if we work through the problem and we get a false equation at the end, like 0 equals 5, that is not true, then the system has no solution. Otherwise, if you work through the problem and all the variables go away and you end up with a statement that's true, then the system has infinite number of solutions. So let's go ahead and take a look at this first one. Both of these equations are equal to y. So using substitution, I can set those two equal to one another. 2x plus 1 is equal to 2x minus 5. Well, if we go through and try to solve this and subtract 2x from both sides, we end up with 1 is equal to negative 5. That is not true. So in that circumstance, this system has no solution. So what that means, if we had graphed these two on the same coordinate plane, they never would intersect, right? If we graph that, we would have two equations or that when you graph them have the same slope, so they're parallel lines. They will never have the same coordinate point. Let's take a look at this one. So if we go to solve this, let's see. I think I'm going to multiply this top one by 2. If I do that, I get negative 4x plus 2y is equal to 6. And I bring this one over, negative 4x plus 2y is equal to... We'll take a look at that. They're the exact same equation. So right there, we should notice that they have infinitely many solutions. But if we don't notice and we continue to solve, well, if we try to subtract these, negative 4x minus negative 4x is 0. 2 minus 2 is 0. 6 minus 6 is 0. So I get 0 equals 0. That is a true statement. That should tell you that this system has infinite solutions. Graphically, if I graph those two equations on the same coordinate grid, they would end up on the exact same line. So every single point on that line solves both systems, both equations, excuse me.